Hey everyone, and welcome back to the channel. Today we are tackling one of the biggest and most important decisions you will make when you're designing any kind of software system, or if you even in a system design interview, which is to choose between a relational database, often referred to as SQL, and non-relational database or NoSQL. Both SQL and NoSQL databases are powerful tools for storing and retrieving data, but they approach they approach this task in fundamentally different ways. Understanding their strengths and weaknesses is crucial for building efficient and scalable applications. This video, we are going to dive into the 7 key differences between SQL and NoSQL to help you figure out which one might be the best fit for your specific needs. So let's get started. First, we start by talking about the data model. Okay. And we start talking about the SQL data model. SQL databases like MySQL or Postgres use a relational data model. Think of your data being like neatly organized into tables. Each table has rows which represent individual records and columns which are attributes of those records. What's really powerful about SQL is how these tables can be linked together using primary keys, which is a unique identifier for each record within this table, and foreign keys, which reference primary keys in other tables. This allows you to establish a clear relationship between different set of data and perform complex queries that join information from multiple tables. How this work? Let's just take an example to understand how this work. So, for example, in a user management system, you might have a users table with user details and an orders table which storing order information. The user ID in the orders table would be foreign key linking each order back to the specific user who placed it. This structured approach is fantastic for applications where you need to perform complex queries and analyze relationships between different types of data. NoSQL, on the other hand, empowers flexibility, non-relational data models. This means there isn't one single way to organize data. Instead, there are several different models, each suited for different kinds of data and access patterns. So we need to look at a few common ones. First, there is key value stores. This is the simplest NoSQL model. Data is stored in a key value pairs, much like a dictionary. You have a unique key and it points directly to a specific value. This is incredibly fast for looking up data if you know the exact key. For our user management system, we could store user information where the user ID is the key and the value is a chunk of user data. For example, while this is super efficient for a simple lookup, this model doesn't really handle complex relationships or allow for querying based on a specific attribute within the value because just value pairs. Next, we have document model. Document databases like MongoDB, for example, store data as documents, often in JSON or similar formats like BSON. Each document has a unique ID and contains a set of key value pairs. The beauty here is that documents can have varying structure, so you don't have to adhere to a rigid schema across all data. Using our user management system again, we could store all information about the user, including their orders, within a single document. This can be very convenient for retrieving all the related information for a specific user in one go. Next, we have a column family model. A column family model databases like Cassandra, for example, also have rows and columns, but unlike SQL, Each row can have a variable number of columns. This model is designed for handling massive amounts of data spread across many machines and is optimized for fast querying on large datasets. Imagine tracking user activity on a website. Each user is a row, and the columns represent actions they have taken, like page views or purchase, for example. Different users might have performed different actions, so the number and type of columns can vary from a user to another user. There is no fixed schema enforcement here. Lastly, we have graph model. Graph model like Neo4j, for example, are all about relationships. Data is stored as nodes, which is entities, and there is edges, which is the connections between them, and priorities and properties as well, which is the information about the nodes and the edges. This model excels at querying and analyzing highly interconnected data. In our user management example that we are talking about all the time, users and orders can be nodes. And the fact that a user placed an order could be represented as an edge connecting them with each other. This makes it incredibly efficient to answer questions like, what are all the products ordered by John? Or who are the friends of Mike, for example? But I would say if the graph model really shines in how can I say it? In something like Facebook or Twitter or any social media networks, like when the relationships is important, so that using the user and the order example, I guess might not be that efficient. But yeah, we have one example, so we want to try to build on it. But you need to know using a graph model is a great opportunity when it comes to using it for a social media platform or anything that when a relationship, it really shines. Okay, next we will talk about the schema structure and flexibility. And we will start with SQL. So in SQL databases, you have to define the schema upfront before you can start inserting any data. This means you specify the tables, the columns in each table, their data types, and any constraints or relationships. This schema enforcement ensures that all the data in your database adheres to a consistent structure, which is fantastic it's fantastic for data integrity, basically, and also great for accuracy. However, this rigidity can sometimes make it slower to adapt to changing application requirements. If you need to add a new column, for example, okay, you often have to perform a schema migration, which can be a complex process, especially in large production systems, and it might even require downtime. On the other hand, NoSQL NoSQL databases in Construct typically offer dynamic or schemaless structure. You don't have to define a fixed schema before inserting data. Different records or documents can have different attributes, for example. This flexibility is a major advantage when your data format evolves frequently or when you're dealing with unstructured or semi-structured data. Adding new fields to some of your data doesn't require alerting the entire database schema. You can just add it to the relevant documents or records. This makes development much more agile in many cases, and it makes your life way more easy. To be honest, way more easy. Next, we want to talk about scalability. We start with SQL again. Okay, SQL databases are traditionally designed to scale vertically. So when we have more machine, we just add more resources to it. Okay, so This known also as scaling up. This means, as we said, you improve performance and capacity by adding more powerful hardware to a single server. Like things like faster CPU or more RAM or more storage. While this can work well for moderate loads, it has its limit. Eventually, you will hit the maximum capacity of a single machine. Furthermore, maintaining the asset properties across multiple servers for horizontal scaling is really complex challenge for many traditional SQL databases. On the other hand, talk about NoSQL. NoSQL databases, on the other hand, are often built with horizontal scalability or scaling out. Scaling out in mind. This means you increase capacity by adding more servers or nodes to a distributed systems. Each node in the cluster handles a portion of the data. So you don't have one server, you have multiple servers that handles. I don't know why I put the servers as circles, but yeah, let's assume that. So again, each node in the cluster handles a portion of the data and the workload, allowing NoSQL databases to handle massive volumes of data and high traffic loads much more efficiently. This distributed architecture also often provides better fault tolerance. In one server, if one server goes down, the others can continue to operate. Okay, and next we will talk about the query languages. We start with the SQL as always. So one of the defining features of SQL databases is the use of SQL, use of structured query languages. This is the standard language for interacting with relational databases. It's declarative language, meaning you tell the database what you want, and the database engine figures out how to retrieve it and send it back to you. SQL is incredibly powerful for retrieving, filtering, aggregating, and manipulating data, especially when dealing with the relationships between multiple tables. For example, to get all the orders placed by users over the age of 25, for example, you will use, for example, you will have to use join, maybe to operate and you will have user join operation to continue to combine the users and the orders table, and also will use where. We'll use this where clause to filter by age, for example. NoSQL, on the other hand, in NoSQL world, there isn't a single standardized query language. Basically, each SQL database often has its own unique query syntax for API, tailored to its specific data model. While this can offer more flexibility and potentially be more intuitive for certain data models, it also means there is a steeper learning curve. If you work with multiple nodes, NoSQL databases, the querying capabilities can also vary significantly between different NoSQL types. For instance, querying embedded data in a document database like MongoDB is different from traversing relationships in a graph databases like Neo4j. It's really different. Next, we want to talk about transactions. So we'll start with SQL. SQL databases are renowned for their robust support, or have known for the robust support of asset transactions. I don't know if you remember the last video we discussed about asset transactions. We talk about automaticity, consistency, isolation, and durability. These properties ensure that a series of database operations are executed in a reliable and consistent manner. If any part of the transaction fails, the entire transaction is rolled back, and once a transaction is committed, the changes are permanent. Okay, permanent. You cannot change it. This strong transaction support makes SQL database ideal for applications where data integrity is absolutely critical. such as financial systems where every transaction must be accurate and reliable. And yeah, we can talk about NoSQL here as well. NoSQL databases often prioritize high availability than um, more than consistency. So you will find it prioritizes high availability and scalability in distributed environments over a full asset transaction support. Many NoSQL databases follow the base model instead of basically um, available soft state and eventual consistent. So there will be some sort of eventual consistent. It will not be high. It will not be high consistent. It will not be um, it will not be as consistent as SQL database. This means that the system aims to be always available for reads and writes, even if some parts of the system are temporarily inconsistent. The idea is that the data will eventually become consistent over time. This trade-off is often acceptable for applications where high throughput and availability are more important than immediate strict consistency, such as social media feeds or real-time analytics platforms. For example, some e-commerce will be happy with that. For example, like if you are going through I don't know, maybe a shopping going through Amazon or something like that. Something like that, yeah. I don't have anything in my mind right now. I'm just I'm just coming out like that. Okay, so I guess next we will talk about performance, speed, and efficiency. We start with SQL again. So SQL databases are highly optimized for handling complex queries involving multiple joins, aggregations, and transactions for smaller datasets and well-optimized queries with proper indexing. SQL database can perform very well, especially for read-heavy applications where data relationships are quite important. However, as the dataset grows and the complexity of joins increases, performance can sometimes degrade, especially if indexing isn't carefully managed. They can also face challenges with very high write loads due to the overhead of maintaining asset properties. NoSQL, on the other hand, NoSQL databases are often optimized for high performance and scale, particularly for handling large volumes of unstructured or semi-structured data. They often excel at high throughput read and write operations, making them suitable for real-time applications, big data scenarios, and large-scale distributed systems. For very large datasets, NoSQL database can often maintain high performance by simply adding more nodes to the cluster, distributing the workload. Their faster write performance is often attributed to their eventual consistency model and denormalized data structure, where related data is often stored together, reducing the need for multiple write operations. Okay, come to the end. Here we will talk about use cases for each. We start with SQL, where the SQL will shine. SQL databases are typically the go-to choice for applications that require first, structured data with well-defined schema. 2, complex queries involving joins, aggregations. 3, strong consistency and asset properties. 4, relational data where the connections between different data points are crucial. NoSQLs will be tend to be better fit for use cases that demands 1, horizontal scalability to handle like massive amount of distributed data. 2, high performance reads and writes for real-time applications. 3, flexible schemas to accommodate unstructured or rapidly evolving data. 4, eventual consistency and high availability in distributed environments. They are popular in areas like social media platforms, Internet of Things applications, big data analytics, and content management systems where flexibility and scalability are quite key. So to wrap it up, both SQL and NoSQL databases have their own unique strength and weaknesses. There is no single better option. The best choice really depends on the specific requirements of your application. If you need structured data, complex relationships, and strong consistency, SQL is likely your answer. But if you need massive scalability, flexibility, and high performance with potentially unstructured data, then NoSQL databases might be the way to go. Yeah, that's it for this video. If you found this video helpful, please like it, subscribe, and hit the notification bell so you never miss any video. And see you guys in future problems, future videos.